My name is Thiel. I'm going to talk about a topic which is called From Data to Knowledge. I'll analyze data and we'll see how much information we can extract from that data. So it will be personal fitness trackers, data that measure temperature, humidity and things like that in your house, electricity consumption and so on, and we'll try to deduce some things and make some models of what we can learn from that. I'm really happy to be able to speak here. This is my first time at one of these conferences here, and it's just great that I can talk a little bit about what I've been doing. This is just a tiny little bit of one project that we're doing, and we've been using extensively for many things the Wolfram language. Unfortunately, I'm not actually going to be able to go into the details of everything. I just want to give you a main idea of what I've been up to. So there are a couple of files I can't actually easily make publicly available because there might be patient data and things like that too. But here's the QR code, so if you want to just contact me, there's the email address as well. We'll put some form of the talk online later. Also, I want to give a special thanks to my co-author here, who's Bjorn Schelter. He's in the second row over there. He works quite a lot with the Wolfram language too, and he also managed to get the money for us to come here, so that's great. Also, he's an expert very much on data analysis, so if there are any complaints about anything you see, just take this QR code, which is his email address, and he'll certainly be able to help you. Okay, one of the things I like about the Wolfram language is, well, my job is basically applied mathematician, so I like modeling things. I like to get data, look at the data, model things. I teach that to students, and we work with industrial partners, with courts and other things to just make mathematics realistic and interesting for all of these areas. So my hobby is listening to people's problems and then trying to make them mathematical and use Mathematica to move that forward. Now, one of the things, one of the common complaints is that when you do mathematical modeling, applied mathematics, that is this kind of thing that you see a cow and you say, well, in order to be able to do anything with it, we probably have to assume that it is a sphere. So because spheres are nice and easy to calculate with mathematically, but I think that Mathematica gives us this unique possibility to do things more realistically. And for example, if we teach, or also if you collaborate with people, it's just nice if you can make things a tiny little bit more realistic. So there are lots of examples how we would do that. So for example, in lectures, what we do is when we look at heat equations, partial differential equations or so, instead of just calculating that on a square or something like that, we would actually take a 3D object. We would usually scan that, even though this is just an example file from Mathematica itself. And then you solve the partial differential equations on that particular surface, and then you can use something like a heat camera and show the students and the people, okay, this is actually how it looks like. Is our model good enough? Do we have to modify and things like that? So that's one of the things that I like, because you've got all these algorithms at your hand. You don't have to always program everything in the first instance. We can make very simple models more complicated. So this is a very, very simple SIR model. You can get a discrete version of it. This here is actually a discrete version. These are the equations. I can probably make that a bit larger, or not. And you can simulate that, and you can actually have sliders, and the students see that. That's all good. But then it's still a very simple, well, school or undergraduate example. So what you can do, and what we try to do in the classes I teach, is you take additional data. For example, data about all the airports in the world. And you can take all these airports and you get, so this is semantic import, you get already the countries and you get the coordinates and the short versions of the airport names and things like that. And then you can find a network and you can actually say, let's assume that they link populations, and let's look at these populations and see how diseases can be spread using, for example, the network of all the flights in the world. Then you can add information about the health systems of the countries, make nearly little submodels of how you think the life expectancy depends or helps to predict perhaps the recovery rate from such a disease and things like that. So we can make models, we can experiment with them very easily. We can then take the data from the countries. Here are different countries, and we actually can look at infection rates and recovery rates for these particular countries. And you see here, for example, Greenland is pretty good because the population density is very low, so it's relatively unlikely that you meet anyone and get infected. And you can make these videos and animations and see how this would spread. Oh dear, this is long now. Okay, so let's do it like this. Okay, so making the models that tiny little bit more realistic, and very often that is based on using appropriate data for it. Now, I think that one of the things when you analyze data and work with people is that you want to tell stories with the data. So this here, for example, is the temperature, global temperature, from January to December for different years, and there's the year, and you see this is the temperatures over the months in the years, and then the time goes up, and you see you're kind of drowning in these lines. It goes up and up and up, and that explains a little bit how the global temperature works. So, how it might change or might not change. You can do, of course, then all sorts of statistics on that and try to explore that with the students. What type of visualizations can we use to tell this story? Questions like those. So the project I would like to talk about today is rather different. And that's one of the projects we do with industrial partners, or we started out with industrial partners at least. And the idea is that if you have certain diseases, like dementia or epileptic seizures or something like that, there might be ways to help you, but only if the disease is recognized quite early on and if you know exactly what triggers it and things like that. So suppose you are developing dementia and they develop drugs to help you, but basically you get a form and you have to fill it in with your doctor, and they show you an image of a pencil and they ask, what is it? And if you don't know what a pencil is, then they say, well, this is bad, and you get medication. But that's late because your brain is already quite damaged. So the question is, you've got something like this called cognitive reserve. So for a while, your brain can actually mask the fact that it loses power. So one of the things we can try to do is we can try to use everyday devices like Fitbits, Apple Watches, Xbox Kinects, mobile phones, things like that. And we can try to figure out whether very early on we can detect any kind of change in pattern, change in behavior. An easy example, it's more complicated than that, but an easy example would be, suppose we monitor your mobile phone and we know exactly where and how you walk, and we see over a year that it takes you longer and longer to find your car when you are at the supermarket, at the mall, and you want to go back to the car, it takes longer and longer. At the same time, we notice that when you write emails, your vocabulary changes. At the same time, we notice that your movement pattern changes, and so on and so on. In combination, we might be able to say, well, something is coming up here. Go and talk to your GP, and with all the data, we might be able to actually treat you early on. So one of the things that is important to do, and for which the Wolfram language is really appropriate, is collecting lots and lots of data and combining the data to make decisions and to see patterns. So this is a very simple thing. I will make this obviously available for everyone. So there is a little device. This is the cylinder here. It's called Netatmo. Lots of people have that. I mean, if you look over the United States, you will see that in nearly every other street or so, people will have such a device. It's a little cylinder. You can have at home, one outside, one inside, and it measures things like temperature, humidity, air pressure, noise levels, pollution levels, stuff like that, CO2 levels in the house, for example. The outside data is made available to the general public, or can be made available to the general public, the inside data not, but you can access it. So we learn lots of things. There are CO2 levels. First of all, it's quite amazing what you can learn about this. You can learn how many people are in your house just based on the CO2 levels, because you see that the changes depend on how many people there are. You can see that when people get sick in their rooms, the CO2 levels will change often. So we can combine that data. We can actually write a little API. So they've got an online access point to the data. And the thing is, I do that here with a little shell script. It's really simple. The only thing why I do that is because I don't want to show you my password in plain text. So it's really easy to do. And basically, the trick is here it generates an access token to the data. And what I do then, let me see whether I've got internet. Yes, I do. So this is basically the entire request. And if you've got your access token already, which you can get from their website, then you just paste it in there. And this particular bit here asks for the temperature on many available stations in Europe in this case. And you see all these points correspond to a station, and the measurements are no older than 5 minutes. So this is the actual time now. We used that, for example, when there was a solar eclipse to just check the temperature drop in different places in Europe and things like that. And it runs pretty quick. Now, I can also do that, obviously, with the data in my house. This is the request. That's my station data. And if I hit enter, I get a little set of icons here, and it's difficult to read, perhaps. Let me see where I can increase some of these. So you would see there's an air pressure of 996, and you've got noise levels. There shouldn't be anyone at home, so this is pretty low noise levels. You've got the temperature, the CO2 levels, and so on. And I can obviously put that in a scheduled task or something and get this data on a very regular basis and can actually follow that up over longer periods of time. So here, for example, the data, this is temperature data. And that's inside. Obviously, Aberdeen is never that warm, so this must be inside. And you see there is a pattern, a weekly pattern. Sometimes it gets lower. You see the houses are not very well insulated either. But you've got these patterns. You can start to try to understand what this does. For example, it's very easy to write with students a little program to heat your house optimally based on these kind of things. These are CO2 patterns in my office. It's my office, and you see I've got usually 5 working days. Sometimes I come in on the weekends too. So I don't only learn how much CO2 I use, I can see how many people are in my office if I look carefully enough. And I can also just detect when I am in my office. The thing is that these data sets are usually not very good. There's missing data, there are all kind of things that can go wrong. The thing is, I can use various devices like my mobile phone, install a little IFTTT kind of thing on it, a little program that measures when I'm in the office. And additionally to the data, I get data when my GPS location of my phone is close by in my office. And again, you would see that some weekends I'm there, but not really often. And some days I actually come in and out of the office quite frequently and things like that. And actually it makes an automatic kind of schedule of what I do. Additionally, I have noise level data. So again, quite similar. The data contains similar information, and by combining all of this, I can learn a lot about my patterns in the office and other things. Your mobile phone, I'll show that in a moment, has about 20 sensors. So we wrote a little program that we can access all the data and stream it to a server if we want. So this is just like GPS data from a phone. I think this is the iPhone data. And you see I just go for a walk, and you see in colors the different speeds I walk around and things like that. That's on the campus. You can also have devices like this. That's a Trachemo. It's a little device that measures the GPS position in all countries in the world, just uses the telephone network and uploads the data to a server, so that in intervals of about a minute or so, I always know where people are. It also has a little SOS button, so if I've got a problem, I can press that and ask the patient, for example, if they need help, how to do this. Of course, I've got data like movement data, so accelerometer data of my mobile phones. I see if I change my walking pattern at one point, they're at about 300. I can see, for example, Parkinson's. If people start moving in a different way, there's a particular pattern to Parkinson patients' movement, so I can detect that early on. And of course, this data is not always good. Here's an interesting set to see just what we have to deal with. This is heart rate data. Basically, I hoped it was measured with my Apple Watch. And you see, at the beginning, up to about here, a kind of different pattern. And that's because I had the first Apple Watch and then got the second one, and they actually measure differently. So that's that change. There's another thing. So if I look at the average heart rate, a little bit averaged over time, you see it goes up, then we've got this horrible dip, and it dips here, so I thought I'd gonna die. But actually what turns out, I got an additional bedded. That's a sensor you put in your bed, and it measures your heart rate. So I basically, when I'm at home, I can tell you for every night exactly when my heartbeats happened. Every single heartbeat. Now the thing is that I didn't have that device at first, and at night, your heart rate is usually lower than during the daytime. So the moment I switched it on, I got these patterns here, which are night patterns, and that meant that my heartbeat dropped down. The problem is that the first bedded I had broke after a while, so there was a time again when I didn't have it, and then I got the second version of it, and now it works again. So we have to deal with these kind of things. That's difficult. That's difficult to see what happened in people's life. I've got Bjorn's data here as well. And I can't, oh yeah, I shouldn't have disclosed that. Okay. Anyway, so he had the first Apple Watch, then he got the second Apple Watch, and in the middle he was on a cruise. And there was he didn't have his watch with him. So there is a gap over there. His heart rate pattern is much healthier than mine. Okay, there we go. So long-term measurements, no problem. The people wouldn't have to care about these devices. It's just basically what you do every day. There is no change of lifestyle required or anything like that. We do something with other devices, like here the Xbox. So that's an Xbox Kinect. We hacked it a little bit. And the Xbox Kinect for the games, they measure how you're positioned in space, how you move. So we get all the data about your position in space. We also get facial information, like whether you are happy or not. We get your pulse rate, and we get all sorts of things. A couple of these Xboxes in your house, and we know exactly how you move. And if these movements, for example, if you shake with your arm because you've got Parkinson's, we see that too, of course. So these are 3D images. That's playing tennis. You can actually use that to see whether your movement is very consistent or whether there are deviations. And this thing is built with an Xbox and a little bit of code in a couple of hours in the afternoon, and you can actually look and try to understand your movements. Of course, it's fully 3D. If you've got a couple of these sensors at home, you can distinguish between different people. You can see how they move, where they sit. There's a nice post about goldfish in a fish tank on the Wolfram community somewhere on the blog. And you see where the fish are in the fish tank. Now with this, you can see where the people are at home, where they sit, how they sit, whether they do anything else. And also, of course, you can monitor whether, for example, an elderly person falls to the ground and doesn't get up. So this thing can automatically send you an email or a text message or whatever you want if your grandfather or whatever fell to the ground. So and that's really easy. In Xbox Kinect, just to let you know about, it's 2 hours, generates about half a terabyte to a terabyte worth of data. Now, we let that run with patients for a year. Then we've got 100, 200 patients. So you can imagine what type of data we have to deal with. And that's just one device. Here's another thing. It's called effigy. It's long code. I'll post the code, of course. Again, a similar thing. You've got a little device that you wrap around the cable, the electricity cable that comes into your house. And it basically, via induction, measures how much electricity you're consuming at that point in time. There is an access code. Again, my password, I didn't really want to put it plain text here on the screen. It hopefully is on my desktop. So I can download the data for a week. It's quite fast. That's the data for a week. There are 2 peaks, one in the morning, one in the afternoon. My wife's working, my daughter gets out. So that's basically in the morning when we make breakfast, and in the evening when we go home. You will see that the times are not actually really matching if you look closely. And that's because now it placed that in US time, and we actually live with UK time, so there is a little shift here, which is the time zones. I can look into details because these data can be measured every 5 minutes or even every minute if I want. So this is just today, and this is live. I mean, this is just downloaded now, so this is what's happened. Oh, God, no. What's wrong with you? So let's go back here. So just look, I downloaded it just before we started this talk here, so you can see this. And you see, there is I suppose because there's 6 hours difference, so there's 6 hours before, that will be the evening data, that will be the morning data. And actually, we trained a little neural network because every single device at your house will make a particular fingerprint on this. So for example, these kind of things, go up, go down, go up, go down, that's my fridge, okay? Now every device does that. So with this, I can tell you, here you put the tea kettle on, here you cooked, here you did this, here you did that. So you get a complete, without anyone needing to log anything. So it's just from that one measurement we can do this. This is our telephone app. So I had a student programming a little telephone app. You can download it from the, this is the one for Android. You can download it and can say what your phone is supposed to measure. You can stream that either to a server or you save that directly on your phone. You get movement patterns. This is me driving home from university home. And actually, I found one where I didn't speed, so 70 miles is fine in the UK. So it took me a while, but yeah, it happens. So you see how fast I go. You see how I accelerate. You see the height. I have to drive over a mountain over there, which is quite true. An interesting question would be, can I detect from just the height profile from where to where I've driven? So taking the road network and things like that. It's a nice game, really. So that's type of typical data I get from the phone: latitude, longitude, acceleration, magnetic field. I get all the other kind of MAC addresses I see. So I can tell you from that with whom you speak and whom you see, because their phones will send you these addresses, and I can say also based on that where you are and what you're doing and signal states and everything. So it's an awful lot of information. One of the critical things here is ethics, because if somebody comes to my house and I've got all this stuff on, I can tell you so many things about them that I'm not supposed to know. And it's really bad if you invite someone for dinner and you say, by the way, you've got a heart problem, go to your doctor. So ethics don't always like that particularly much. So time is running very fast, and I'm probably not going to get through everything I wanted to say. Let's make this here a bit smaller again. So the interesting bit is that we can combine all this data, which is measured in different time scales, different sampling rates, into one single system with the Wolfram language, because it's so flexible about how you store data. That's a very powerful thing. So here, we've got EEG data, and we've got movement data from the Xbox. Now, what happens is that usually we implant the electrodes, but sometimes, well, just to show that this can be done differently, we actually have here an extracranial EEG, and we have Xbox data. Now, the thing is, when your muscles move, when you move like that, you get huge spikes in your EEG signal, because the muscles produce electric signals. And that makes the signal basically useless, because you see a signal here, this nice going up and down, that's my 50 hertz, that's just the electricity. Here, I move a little bit, and you get out of control, you don't actually get any kind of useful signal. And what you would usually do, and the code is all in here, so you can see how this works, you would get a notch filter. For example, you filter out the 50 hertz frequencies and other things, and you get something like that there. And you see at the beginning, it looks like that, but still you have these very, very large artifacts. Now, Bjorn is a magician in terms of data analysis, so we use state space modeling to actually get rid of these artifacts, to clean up your data. So this is the cleaned up data based on a little bit of code. The code that will be in the workbook that you can download in the notebook will not be the complete one. It will not run in real time. It will take about 5 minutes for a 10-second signal or something like that. Within the Wolfram language, without anything else, we managed to get it in faster than real time. And I think that's the first time that algorithm, or any similar algorithm, could be done in real time on all the electrodes in an EEG and lots of other movement data. Now, this thing learns from the movement data, because it's got the Xbox data, that I'm moving here. And that allows the program to know these are artifacts, filter them away. Okay, so it's a very powerful kind of analysis tool. And that's just one of the hundreds of examples that we need to make the signal nice and clean and usable, because these data points are not really always very good. Now, here's just a simple example. That's a naive Kalman filter. It's slightly different than the Kalman filter that's implemented in the Wolfram language. So what I do is I generate a signal and add noise to it and spikes. So basically, I then run it through this filter, and what we get is kind of like this. So the time series with noise is the blue one. You've got these large spikes. The Kalman filtered is the orange one, and the green one is the original one. So it basically, this is a very easy case, because it filters away just the spikes. But even if there is observational noise or other types of noise, it just filters them out. Additionally, I can use all these other data sets, like movement data, heart rate data, everything else, blinking data, whether you blink, and I can use a combination of that, and this program will basically tear these things apart, use the information, and filter out what you have to do. Now, there are just a couple of seconds left. So let me just show how this at the end works. So this is a spectrogram of the original data. You see the 50 hertz, and you see lots of artifacts. This is a notch filter. It gets rid of the 50 hertz kind of line, but it basically makes a bump there, so you filter out too much. And if I look at the estimated spectrum, this is how it looks. Now, what that means is that I can now use, for example, movement data and brain data. This here would be artificial spikes in the data that I can't use, and it would filter the brain nice and clean, so that even from external electrodes, you get a very, very clean signal that you can actually use, for example, to work on epileptic seizures and things. We can do networks and stuff like that. There's one last thing I just mentioned because I'm over time, and that's we can, of course, use machine learning, for example, to detect automatically different patterns. For example, you say, person is standing, brain activity is such and such. Person is sitting, brain activity is such and such. And it gets these kind of different states out automatically, basically. So I don't have to really go by hand through all the data and say, what does this mean? but I can classify it into different categories and can basically tell you exactly what the person is doing at home. And here, this, for example, is a completely artifact destroyed kind of system. I can ask, it's very easy because it's all built into the language, of course. I can make little questionnaires, and I can ask the patients or people who use the system for input. So it's a little questionnaire like that. I can ask any questions. This is collected in a database. I can analyze the data, pain levels, and I can ask for that. I can interrupt this. So if people get an epileptic seizure, I can just before write them a little text message, say, look at your phone, play this game, do something else. Perhaps that helps to prevent the seizure because you actually do something really different. And last but not least, there is a little thing we also wrote. That's feedback to the user. So basically, we use push bullet, which is also in Mathematica directly, to have an automated system that can send this type of information to the user. So we can say, look, something is coming up in your brain waves, do something else, take a pill, do this, do that. And of course, there's a complete protocol of everything that's happened. The doctors can be informed immediately, family members can be informed, and so on and so on. So these are cases where we use lots of data combined. It's just a tiny, tiny fraction of all the data we use. We use data about your driving style. A little device that plugs into your car, and we see how you accelerate. Are you aggressive when you drive or not? So I think we can do approximately 100, 150 different sensors at the moment. And that, of course, produces an awful lot of data that we have to analyze. Thank you very much.